Let us consider an example circuit and try to go through the process of finding the Norton equivalent. Consider this circuit. This is a DC circuit. Therefore, all the impedances can be considered as resistances. Now here in this circuit, this is A and B, the output terminals of interest. All these parts of the circuit are the fixed part of the circuit for which we would like to evaluate the Norton's equivalent. You have a current source here and a voltage source here. So there are two sources. So let us give some values to these resistances and the sources. This is a 1 amp source with the current direction indicated like this, 10 ohm, 5 ohm, and a voltage source, 10 volt voltage source as shown. So our objective is to find the Norton's equivalent. So first step is find Z0, the Norton equivalent impedance. In this case it is R nor because all are resistances. So just like we do in the Thevenin's case, keep AB open circuited. Next, if there are voltage sources, short all voltage sources. In this case there is only one voltage source, this is a 10 volt source which we need to short, and open circuit all current sources, and in this case we have one current source which is the 1 amp source as shown here, and then redraw the circuit for evaluating the impedances. So this is the redrawn circuit. Notice that we have short circuited the voltage source and we have open circuited the current source. Now how to find the impedance as seen from the terminals AB. Now this open circuit can be replaced by a resistance of a very large value or infinite value. So let us say we include a resistance which I have shown in red here of value infinity, very large. Okay, now this network we can solve easily. So consider this two resistances, they are in parallel. Parallel means the equivalent resistance is product by sum, 5 into 10 by 5 plus 10. So it is about 3.33 ohms. So replace that by a single resistance, 3.3 ohms. Then you have this very large resistance in infinite value. Then you have 5 ohms. And this is the 10 ohms which you are placing it here. A and B. So if you consider these resistances which are in series, it is 3.33 plus infinity plus 5, which is same as infinity. So you can, because this large value resistance swamps out these two values which are insignificantly small compared to this, you can say is approximately infinity. So this can equivalently be written as two resistances in parallel. One is infinite and another is 10 ohms, which is this, and these two equivalently will give you the Z nor in infinite value, large value, into 10 divided by 10 plus that very large value of resistance, which is approximately 10, because this infinity and this infinity together will cancel out. So it is 10 ohms, and this is the Norton equivalent impedance. Next, let us find Norton current. By inspection you can see here that we need to short this and find out what is the current flowing through the short circuited output terminals. So let us make this short and let us see what is the current that flows through this short. Here you see that by inspection 1 amp is flowing in this branch which divides into this 10 ohm path and the output path. And because the output path is short circuited, it swamps out this 10 ohm path, and all the 1 amp flows through the output short circuit. So the output short circuit current is 1 amp. This also implies that I0 or the Norton equivalent current is IAB at short circuit, which is 1 amp. So this is the Norton's current. So now we can write down the Norton's equivalent circuit for the circuit shown above in this fashion. So the Norton current source has a value of 1 amp. The direction as shown here. The Norton's equivalent resistance R NOR is 10 ohms, and together they form the Norton equivalent circuit for the circuit shown here.